Good evening, everybody. I just thought I'd just keep going. I just did the lab. So this is going to be 7.1. This is the start of the stuff for the last exam, test three. So obviously this is where it gets a little more tricky, a little bit more complicated, and all of that stuff. So I'm going to try to take this really slow. And if you need my help, guess what? I'm here. Shoot me an email. And I'll do whatever I can to make this make sense for you. So I'm sharing my screen. If you go into the notes, you'll see we have 7.1. The first 7.1 is estimating population proportions. Okay, so this whole 7.1, 7.2, 7.3 stuff, this is going to be a little bit different. This is going to change some stuff. So I feel like this is the one that might be more challenging before we get to the end, right? But here we go. So I'm going to go right to the textbook. Usually I do a little bit of intro stuff, but I'm just going to go to the textbook and work my way through it. Okay, so here we go. 7-1. Here's how it starts. Basically, our whole goal is to estimate what's happening in the population. So can we take our data? Can we take what we know and generalize it? This is like making a type 1 or versus a type 2 error in statistics. Here we go. So a type 1 error occurs when a null hypothesis is incorrectly rejected, while a type 2 error occurs when the null hypothesis is not rejected when it's actually true. What does this mean? So here we go. So the false positive, and then we have the correct decision, but it's true positive. So if we reject it and it's false, we're good. If we don't reject it and it's true, we're good. But this is where the errors come in. So the type 1 is we think something is true, right? But we have to reject it. And this is where we don't reject it, but it's actually false. This is what happens with this whole idea, right? It's definitely what's going on when we're trying to make sense of it. If you want, this is great. Obviously, this is the organic chemistry tutor guy. I think he's really smart. So if you want to watch his stuff about it, that's okay. But we're going to get here. We'll definitely get here for hypothesis testing. But our whole idea is we're getting these answers, right? And we have to see, can we generalize this answer to the public, right? Can we estimate what's going on in our population? Are we able to do that? Are we able to do it? That's, oh, sorry. Hypothesis testing's an 8, but this is obviously the precursor to 8. So let's get right into the book. This actually focuses on the population proportion, but we can also work with probabilities and percentages. When working with percentages, we will perform calculations with the equivalent proportion value. Here are the 3 main concepts. Okay, we got a point estimate. The sample proportion is, that looks like a delta to me, the best point estimate or single value estimate. The confidence interval, you can use a sample proportion to construct a confidence interval of the true value of the population proportion. We should know how to construct and interpret it in the sample size. We should know how to find the sample size necessary to estimate a population proportion. So these are the 3 ideas that we kind of have to know as we go through this. So I might as well write them down and keep them here for us. So we have a point estimate. Which is basically what is the best estimate or single value of the proportion of the population. So we need a basically the best or most accurate value of the population proportion. Okay. Then we've got our confidence interval, and this word we will see a ton. This thing is going to come up for the rest of the course, okay? Like when I say we have to be 95% confident, that's the confidence interval. So what does this mean? We should estimate the true value. This estimates the true value of the population proportion. So we'll talk a lot about this. Okay, this one's going to come up a bunch. And finally, our sample size. Well, that's just our n. That's just like how many people we got. So this is just our n right here. And this is, we should be able to find the sample size necessary to estimate a population proportion. This is actually really close to G-power analysis that I spoke of before. The G-power analysis just kind of tells you how many people you need. The G-power analysis is basically just telling you what do I need for my sample size to do stuff, right? How many people do I need in order to get a good result? And this says we need to know how to find the sample size necessary to estimate a population. The concepts presented use the following, so it's important to understand it quite well. So here's our notations. We might as well have it. X is success. N, that's our sample. Big N is population. This P with the hat on it, which we know is our what? In case you forgot already, the point estimate. We're going to find that by taking X, the successes, and put it over N. So this is our point estimate for the sample proportion. And then our little p is X over big N, strange notation, and this is our population proportion. All right, so these notations are going to help us out a lot. And we're looking at probably some crazy formulas. Part one, point estimate, confidence interval. Okay, well, that's basically what we're doing. So we want to estimate the population with a single value. The best estimate is the sample proportion because this consists of a single value equivalent to the point on the line. All right, so it's a single value used to estimate the population parameter. The sample proportion is the best estimate of the population proportion. Unbiased error. We use sample proportion as the point estimate of the population proportion because it is unbiased and it's the most consistent of the estimates that could be used. So we're using the exact one from the sample to represent the population because we feel like there won't be any bias in it. The value of the corresponding population parameter in the sense that the distribution has a mean that is equal to the population parameter. The statistics targets the population proportion. The sample proportion is the most consistent estimator of the population proportion in the sense that the standard deviation of the sample tends to be smaller. Okay, so we want to just use the sample to try to lose the bias because we won't have more variation. By using the sample, the small group instead of the big group will have less bias, which means it will be closer unbiased estimator of P. Sweet, so we get an example. The chapter problem included reference to a Sallie Mae survey of 950 undergraduate students. 53% of them said that they take online courses. Based on the result, find the best point estimate of the proportion of all undergraduate students who take online courses. So we're going to use the sample. Why the sample? Because it's a better choice and should not have bias. So our sample is what? The 950 students. X is the success, is what we want. So what's our success? In this case, it's going to be 0.53 or 53%. And all I have to do is take P and take the 950 and divide it by the 0.53. This should give me what I want. All right, so this gave us 1,792.45. This does not seem right. So let's look at it. Because the sample proportion is the best point estimated population, we can conclude that it is 53%. Oh. So I guess we don't need to actually do any mathematics or formula. As I said before, the mean from the sample is the best one. So our best choice is just 53%. Very tricky, very tricky. All right, let's keep going. All right. Why do we need confidence intervals? Perfect. All right. Something that is familiar to me a lot, very familiar to me, that I use all the time. So in example one, we said that 0.53 is our best point estimate with a portion P. We have no indication of how good that best estimate is. This is our best guess. We have no clue how it is. By giving us a range of values associated with the probability, confidence interval gives us a much better sense of how good an estimate is. Nice. So usually our confidence interval for just about everything I've ever done in statistics and research has always been 95% sure. That's an alpha level of 0.05. This means I'm 95% sure that we are between what? 2 standard deviations of our mean. And that's how we know that we're not, if we're outside of this, we are 95% sure that guess what? This wasn't due to chance. This happened for a reason. It's that far away. To me, that's what a confidence interval is. It's the range, right, of the values used to estimate the true value of a population. Confidence interval is sometimes abbreviated. See, I use CI all the time. So here we go. Here's an example of a confidence interval illustrated later in example 2. 95% confidence that the interval estimate of a population is between 0.499 and 0.562. What does this mean? This p-value, and if you forgot what p-value already was, the population proportion has to be between 0.499 and 0.562. We're 95% sure. So the 2 key elements of contour are 1, the levels that are associated with the critical value, remember from before, and the margin of error. So the confidence interval is the probability of 1 minus your alpha level, that the confidence interval actually does contain the population parameter. So assuming that the estimation process is repeated a large number of times, the confidence interval level is also called the degree of confidence or the confidence coefficient. I've never heard it called the confidence coefficient. So here we go. The following shows the relationship between the confidence level and the alpha level. All right, 90%, usually never okay in research. This is never really used. 0.95, that's all your social sciences. That's your psychology, all your psychological studies. That is for all your observational studies, things like that. This one, alpha level is 0.01. That's all your medical studies. So that's like everything you're going to see in nursing and medical journals. We're not over 99% sure. We don't want to do that treatment. We can't trust it. So that's how those work. I don't know why they got 90 here. I don't mind. So after selecting the confidence level, the associated critical value must be determined. The sample size, the sample proportion, error. We will use the following definition of critical value, which first presented, and this definition uses a z-score for the standard normal distribution. Cool. So this is what they're trying to say. We got critical values, or CVs, right? Our critical values relates to those z-scores, right? So they relate to the standardized probability. And we're cutting them in half. This is always done when it's 2/10, right? So this is our alpha level divided by 2, or alpha level divided by 2. What does this mean? What does this mean? We are our alpha level, whatever values we pick for these gets cut for us to be significant. As long as we're cut over here, we are confident that it's going to fall in this range. You can make your alpha level whatever you want. Usually our alpha level is going to be 0.05, which makes both of these what? 0.025 and makes this a negative 0.025. That's what we're probably going to be working with for just about everything. For a standard normal distribution, the critical value is a z-score on the borderline, those that are significantly low. Here's your significantly low side. Here's your significantly high side. The number z alpha over 2 separates the area to the right tail and the normal distribution. Figure 7-2 is a 0.05. And then divided by 2 is, for alpha is 0.05 when we plug it in. We got 1.96 for both of these because that's the critical value. And there's exactly how I had it. The 0.025, the 0.025, because these are z's here, that's why I should leave it as the z-score instead of the percentage. This is 2.5%, negative 2.5%, negative 1.96, 1.96. So this means we're just using this. How sure are we? We are 97.5% sure on that boundary. Note, we use a cumulative left area of 97.5%. So if we're confident at 0.05, the right tail is 0.025. So we just want everything to one side. We want just everything from this side. With an alpha level of 0.05, we can be what? 97.5% sure it's not due to chance. I keep saying due to chance, because we never know. We'll see more about that in hypothesis testing. So there's the 1.645, the 1.96, and here's the 2.575. That's what your z values are going to be. That's what these little numbers are. If you forgot how to do the z values, just watch the previous video. All right, error. Because this is us doing stats, there's always going to be error here. Okay, so for our error, when using this sample statistic to estimate the population parameter, the margin of error E is the maximum likely amount of error at which the sample statistic misses the parameter. So can we be off? Yes. How can we be off? If our sample stat is not the same as our population stat. Like right away, we're saying this is the best mean. We got to use this sample. We're using the sample, tell us stuff about the population, but we could miss. If it's off, that's our error. So we always have to account for how much error we have. Okay. And the margin of error can be found by multiplying the critical value and the estimated standard deviation of the sample proportions. And this estimated standard deviation of the sampling distribution is called the standard error of the sample proportions. All right, so I might as well show you what this means. Okay. This is our first crazy formula. There'll be a few more, but here it is. So here is our error, right? This is our margin of error. We have our z-score, but we take our alpha, we divide it by 2. Okay, this gives us our what? This is our critical value. This is what we're testing. We want to make sure it's above it. Then I multiply this by the square root. Now, what is P? What is Q? And what is N? So this says it's the estimated standard deviations of the sample proportions. It's a little bit of a stretch. I think about the P in this case, or most of the P, as what? This is our successes. So the P is what? The entire sample proportion of successes divided by N. That's what the P is. What's the Q? The Q is it not happening. So we're basically taking both of these. We're taking this, which is our successes, multiplying by what? It's failures, and then we're dividing it by N. That's really where it comes from. But I'll take it. Estimated of how much you deviate from the mean, that's fine. All right. The walled confidence interval. I don't know this one. So when constructing confidence, you're using the margin of error E given in this formula. There's a result. Oh, okay. Is the walled confidence interval. Part 2 of this section will discuss other methods. Alrighty. You must be careful to interpret the confidence intervals correctly. There is a correct interpretation and many different and creative incorrect interpretations of the confidence interval. Okay, so what does it say? We are 95% confident that the interval from 0.499 to 0.5, so 0.499 to 0.562 actually does contain the true value of the population proportion. Yes, I feel like I've said that a bunch of times. This is a short and acceptable way. It's like many different samples, different random samples from 950. Okay, that makes sense. The success rate. Okay, yeah, this is not the true value. All right, so they're saying that the true value will fall in between. We have to say that we are confident that this interval does contain the true value. And then this is saying that the chance that p will fall in between this. So it's not a fixed value. Like all of this, right? They're right. It varies. We're not really sure how many people we have. We're not really sure what our n is. Like we don't really know until we actually start sampling people how many people we have. So that's why we have to be very specific with our language. We'll fall between this. Okay, it's basically saying the same thing twice. Confidence level tells us the process we are using should in the long run result in the confidence interval limits that contain the true population. Suppose the true proportion of undergraduate students of an online course is actually 0.5, which shows that 19 out of 20 or different confidence intervals contain the assumed value of 0.5. Is figure 7.3 is true. 95% we expect 19 out of 20 confidence to contain the true value. This constant does not contain it. So this is why we can be so sure that most of the time we're going to be right. It's not like a guessing game. It's just like we're trying to make the best estimated guess based on our data. Construct a walled confidence interval. Okay, so we have our notation, we have our sample, we have our number of sample values or margin of error, our critical value. Okay, so this is all of our notations. So what does it have to be? A simple random sample, a binomial distribution, so a fixed number of trials, so it's got to be a yes or a no, or a success and a fail. There's at least 5 successes and at least 5 failures. Okay. And if this requirement is not satisfied, one alternative is a bootstrap pre-sampling method. All right. P minus E is less than P, which is less than P plus E. So what is this? What does this mean? Our point estimate minus error is the population proportion, which is less than our sample population, right? Our point estimate plus error, where the margin of error is that formula. This confidence interval is also expressed in 2 following formats. Plus or minus error, or same idea, minus error plus error. So we're going to go to 3 significant. So 3 significant digits for this. All right. Verify that the requirements in the preceding key elements are satisfied. Use technology or A2 to get the critical values. Evaluate the margin of error using the value calculated. All right, so we'll get the upper and lower limits. Round to 3 significant figures. So this is the process, right? So in order to do one of these, right, in order to get this confidence interval, where we're sure of what's going on in the data, what do we have to do? we have to make sure it's what? It's a simple random sample. There's more than 5 yeses, 5 nos. It's either it's either a success or a failure. It's a normal distribution. Like these are things that we have to make sure first. Then we have to find our critical values. Usually it's going to be this 1.96, right? It's usually going to be this value every time. Then we have to use this formula to get the margin of error. Then all we have to do after all of that work is take this P, right? The sample over the N, and do what with it? Add the error and subtract the error. I know it's a lot. Sounds crazy. I think once we do an example problem, it's going to make sense. Finally, an example problem. So let's have this thing make sense for us. Okay. In the chapter problem, we noted that the survey had 950 undergraduates, 53% take online courses. The sample results are 950. And then we have this. What was this? This is the point estimate, or the best value is going to be 0.53. So we got to find the margin of error for 95%, the confidence estimate for 95%, more than 50%. So in order to do this, we have to try to be like, okay, they probably did simple random sampling. Is this a fixed number? Like we have to really make sure of all of these pieces before we even get started. Before we even do all these points, the first thing we have to do is kind of make sure all of these requirements are fine. If we don't do this, if it's not successes and failures, if there's not at least 5 of both, 5 people who said success, 5 people who said failures, we can't do this. We have to do what they call bootstrapping. I've always referred to it as like modified CIs, but that's what we have to use. So now all we have to do is get the technology, okay? We have to figure out what this is. So they say stat disk, but are we going to use stat disk? I don't want to use stat disk. I want to use like our brains. Because every time I try to use that stat disk, it never works. So we're just going to do the formula. The formula is not crazy. It's just this. We just need the E. Once we get the E, we're fine. So to get this value for your z-score, the first thing you have to use is understand what we're talking about. They said 95%, right? So if we know we have 95%, and if we actually go backwards, normal dot inverse, right? Norm dot inverse. And we have 0.95. And we have a mean of 1 and a 0 for standard deviation. We should get that value. Our ability, our mean is 1. Oh, sorry, I have it backwards. Our mean is 0. Our standard deviation is 1. Sorry about that. So this is the normal curve. 0 is for your mean, 1 is standard deviation. I just wrote them backwards. There's our 1.64. Okay, that's how we can get it right away. We have 0.95. That gives us that 1.64. That's the first number we need to start this thing. Okay, that's where it comes from. So 1 point was 1.64. Yes. All right. So there's our 1.64. That's what we're doing to start with. That's our first value. Okay. Now we know our N is the 950 trials. We have 53% yes. And then Q's got to be the other side, right? Nice. See, this is what I'm meaning by yes and no. Like when they say estimated SD of the population, like to me, that doesn't make any sense. P, you could always think about success, or it's a yes, it's the percentage. And Q is the failure. This is us not happening. So that's why when they say estimated SD of the sample populations, they're not really telling you what they are. It's just this times the square root of yes is 0.53 times no, which is 0.47. And how many people do we got for this thing? Our N is 950. And that's all we're going to do. We're just going to drop it in. So 1.64 times. And I need a square root sign of, oh, well, this is where I need the parenthesis, but that's okay. I'll just put a second one. 0.53 times 0.547. We're just going to divide this whole thing by what? 950. This is why I didn't need this second set of parentheses around the outside, but honestly, I'm cool with it. 0.0266 is what I got for my E. That's the value I got. Let's see what they got. They got 0.031. 0.031. Okay, because I did 95%. And it's not really 95%. Why is it not really 95%? Because of that little subtraction move they did. It's 1.96. This is if I wasn't including it, but we have to use 1.96. So if I make this 90, what was it, 97 and a half? I believe I'll get this 1.96 that they want. Yep, there it is. Why does it have to be this? Because it's everything below. The 5% gets cut in half to 2.5, and we only want everything less than 2.5. What am I trying to say? We're dealing with 5%, right? Our alpha levels. So I have this picture, but we're here and we're here. So this alpha level gets split into 0.025 and 0.025. And I just want everything that's less than this. So this is not 95% of my curve, right? This is 0.975 because it includes the whole bit. That's why it's 1.96 times P times Q over N square root of that. It's okay. We all make mistakes, right? There it is. 0.031 or 317, I believe. We want three significant figures. .0317. Ta-da! So what does that mean for us? We have this 0.0317. I guess they're using one more. I can use 4. Doesn't matter. But basically, we're going to be confident between what? Minus E. This is our mean. Basically, this is just going to be the mean that we want. So this is our success of it happening, which we already know that we got, which was the point, I believe it was 0.53. Yeah, 0.53. That's what this is. And then it's going to be this bit plus the E. So all I have to do is take this value. We have to add this to what? 0.53. Ta-da! And all I have to do is 0.53. Oops. .53 minus that, and 0.498. I believe it's the exact answer that they've got in the book. That's how you get it. 0.498, 0.562, ta-da. So we're 95% confident that this value, or the setup of these values, are going to fall between 0.498 and 0.562. The reason for this discrepancy of the manual calculations are based on the critical value being 1.96, but it's actually 1.9599. And guess what we got? 1.9599. So it is what it is, right? It is what it is. Based on the confidence interval obtained in Part B, we cannot safely conclude that more than 50% of the undergraduates take online courses. Because the confidence interval ranges from this to this, it is possible that the population percentage is below 50%. Okay. Yeah, that is below 50%. I believe that. I'll take it. We're saying it's between 49% and 56%. So I'm fine with that. And here is one statement that summarizes results. 53% of undergraduates take online courses. The percentage based on this selected, in theory, 95% of such polls, the percentage should offer a difference by no more than 3.2 percentage points in either direction. That would be found in both. Nice. So this is the value. This is how off we could be. That's our error. We're saying 53% plus or minus 3%, 3.2. So it's pretty close to 50%. I don't like to say, but I'm human. All right, so this is if it doesn't work. There will be times when, especially with working with errors, when things don't work. Section 7-4, which we'll get to, I'm assuming. Constructing confidence on the population parameter. The basic approach is to use technology such as that is to resample the sample data many times and use a sorted list of 1,000 results to find the confidence interval. If we repeat example 2 using the bootstrap resampling method, here's a typical result. 0.498 to 0.561 is the randomness used in the procedure. The result may differ. All right. Example 2 deals with a specific poll. So it should be a simple random sample. Confidence interval should be provided. The sample size should be provided. And except for rare cases, the quality of the poll results depend on the sampling method and the sample size, but the size of the population is usually not a factor. Okay. Caution. Caution, caution. Never think that a poll results are unreliable if the sample size is small. As I keep saying with G-power analysis, it could actually be really small as long as it's done the right way. It'll tell you exactly how many people you need. The population size is usually not a factor in determining the reliability of a poll. That is true. It is true. All right, let's see what we got. Finding the point estimate and E from a confidence interval. Sometimes we want to better understand a confidence interval that might have been obtained from a journal article. This is the first real stuff. It's the best paragraph we've had in 7 chapters. Sometimes they just give it to you, but you don't know like how they got the numbers, so this is going to show you how to go backwards. All right, so if we want to get the point estimate, well, finally something useful. We do the upper confidence interval, so I'm just going to put CI with a little u plus the CIL, so upper versus lower. So we add them together and then we just divide it by 2. And the margin of error is going to be the upper confidence interval minus the lower confidence interval divided by 2. I know it's really simple formula, but at least you can work backwards. So let's do one of these working backwards with how do I get rid of this box? All right, the article High Dose Nicotine Patch Therapy by Dale Hunt includes a statement of the 71 subjects, 70% were abstinent from smoking for 8 weeks, 95% confidence interval, 58% to 81%. Use that statement to find P and E. So basically to get P, we already have this. So we already know it's between 81 plus 0.81 plus 0.58 divided by 2. That's all you got to do. I got a parameter of 0.695. Let's see what they got. Sweet. And the margin of error, we're going to do the same thing, but we're going to subtract it. Finally, something really useful. 0.81 minus 0.58 divided by 2. So I'm just going to go right back to my formula, change this to a minus sign, 0.115. That's how much error we have. Nice. All right, and final. Confidence interval can be used to address some claims made on the population proportion. This is the most important thing. This is what we really use it for, or the time I've always used it. So, for example, consists of 70 heads and 100 tosses. The resulting confidence is between this and this is evidence supporting the claim that the proportions of heads is different from 50% because what? 70 heads out of 100 tosses is saying that it's between 0.61 and 0.79. It's pretty interesting. I kind of like it. It just depends on what you have. Like, it's saying that because of this sample that we used, it is different from 50%. But obviously, it's just the sample. Determining the sample size. Did they give you G-power analysis? They do it the right way? Okay. We must first determine the sample size, which is the number of sample units that must be collected. If we solve the formula for the margin of error for the sample size n, it requires P is the estimate known. But if no such estimate is known, as is often the case, we replace 0.5 and replace Q by 0.5 in the resulting formula. Will give us the same. Okay, that's fine. This is the way that they're saying to do it. I would use a statistical program, but as long as it's a 50-50 shot, we can use this to figure out how many people we need. So the population proportion, the number of sample values, the sample proportion, and desired margin of error. And then we've got some formulas. Cool. So not bad. Not bad. This is not bad. So when we know P, so when we know what it's supposed to be, right? So when we have like this parameter, right? Like, so if we know for what we should have for our mean, it should just be our critical value. That's the Z alpha divided by 2. That's our critical value. We're going to square that to make it positive. That's the whole point of squaring it. This is the yes, it's happening. This is the no, it's not happening over whatever error we have squared. And this is when we do not have no estimate for that value or for success. No estimate for successes. If you just want to think about successes and failures, this is not P. This is N. This is how many people we need. So it's Z alpha over 2 squared. And this is basically us doing what? We're claiming that P, it's the 0.25 this quarter is just claiming that P is 50%, it happening, and Q is 50%. It's not happening. That's how we get that 0.2, that quarter, that 25%, and then we just divide it by the error squared. We're just automatically, arbitrarily cutting this to 50% yes, 50% no, if we don't have it. Nice. Now we round. You always round up because this is like people. You can't have 0.135 of a person, so you're going to go up. You always round up for sample size. Cool. So just remember that. Round up for sample. Let's keep it going. All right, so we've got the Pew Research Center, 470.87, selected from 79% shop online. So that's our P right away. That's our P. If we want to, that's our success. That how many adults must be surveyed in order to have a 95% confidence interval. Okay, so here we go. All right, so we're going to use this formula, and hopefully I can make it as clear as I can. So we want to be 95% sure. So N is what we're looking for, right? N is what we're trying to find. The first thing we need, 95% sure. If you don't memorize that formula, right? Equals normal dot INV. And our probability is 0.975, because what do? We cut our 0.95, our alpha is 0.5 cut in half, and we do the opposite. That's where this 0.975 comes from. Our mean is 0, standard deviation is 1, so our value is going to be that 1.96. 1.96. Now, our P is yes, this thing is happening. So what is our P in this case? 79%. So if yes is 79%, oh, we have to square it. If yes is 79%, no has to be. Again, if you can't do any of these in your head, don't worry about it, right? $100 minus 79. Don't be ashamed, right? It's 21. So this is 0.79. This is 0.21. We're dividing it by the error squared. Now, did they give us the error? Let's look at the question. What's our error? How'd they get the error? The margin of error is 0.03, which is equivalent to 3 percentage points. Where does it say that? The upper we don't have this yet. We don't have the confidence limits. Can we just claim that the error is because we have 3 of these? I already don't like it. Error is, okay, perfect. Here's the error. But we can't find the error without the sample size. So they're claiming it's just 0.03 because there's 3 significant figures, right? That's all that they're doing. I already don't like it. Oh, never mind. It says right here. It's by no more than 3 percentage points. I guess I didn't read the problem. Sorry. So no more than 3 percentage points. That's why it's going to be 0.03. It says percentage of this. So it's 3 percentage points, 0.03, 3%. Then what do we have to do? We have to square it. Ta-da. I didn't read the whole question. Sorry about that. So we know it's going to be 1.96 squared times 0.79 times 0.21. Then all I have to do is put a parentheses around it and divide this by 0.03 squared. So this gives us how many people we need. How many people do we need for this survey? 709, not 8. We cannot have 13% of a human. I don't care how bad they were mangled. So it's 709. Ta-da! Assume we have no prior information suggesting the population one. So if we don't know, the only difference to the formula is we just make these both 0.5. That's it. We don't have it. This is 0.5 and this one's 0.5 because we make it 50-50. So how many people do we need for B? 1,068 people, assuming that's what they get. Ta-da, 1,068. We did it. Caution, don't make the mistake of using 3 because it's percentage points. Duh. If I saw it and read it, I'd be better. All right. So assuming we're at the end, log coverage probability is to the row. Concept used to gauge the quality of confidence interval is the coverage probability as followed. All right, I don't know what this is. Coverage probability of a confidence interval estimate of the population proportion is the actual proportion of such confidence intervals that contain true population proportion. If we seek a specific interval such as 0.95, we would like to get that actual coverage. Okay. Actual proportion of the population that contain the true population proportion. Okay. So the +4 method performs better than the wall. So we add 2 to the number of successes, add 2 to the number of failures. So the trials is going to increase by 4. And then we have the Wilson score, which looks a little crazier, which I don't think we're going to do. Which method is best? I don't know. If anybody wants to see me work this one out, guess what? Email me. I think this one is good enough for me. Let's jump to the questions. I know that was long. This is probably going to be the longest one of this section, but at least it makes sense. All right. Let's knock them out. 1 through 6, 11 through 14. Here's number 1. The USA Today provided results from a survey of 1,144 Americans who were asked if they approve of Brett Kavanaugh as the choice for Supreme Court Justice. I didn't think he was such a bad guy, but you can hate me if you, because I said that. 51% of the respondents said they did not approve. They did approve, and the margin of error was given as a plus minus 3.5. One important of the element was omitted. So what did they omit for what? Got all this information. I don't know. Oh, there's no confidence interval. That would be nice. I'm assuming that's the answer. All right. Did the poll describe next exercise 1? Describe what is meant by the margin of error was given as 3.5 percentage points. Well, if you don't understand what the margin of error is, that margin of error is basically all the successes, the failures over n times critical value. But that doesn't really mean anything, right? This means we are sure, whatever the confidence is. They don't give us a confidence interval. But basically, for number 2, this means the 51% of respondents who said that they did approve is really between what? 51 plus 3 is 50 what? All right, get confused. I always want to do this no matter what, just to make sure I'm not. It was 3.5, right? 51 plus 3.5, 54.5, and 51 minus 3.5 is what? 47.5. So really, we're between these two numbers because there's error. So even though it said 51% approve, it's really between these two. That's what it means. All right, let's jump to 3. For the poll described in exercise 1, what values does P, Q, N, and E and P represent? If the confidence interval is 95%, what is the value of A? If that's 95%, your alpha is 0.05 or 5%. That one's easy. Your P, this is our successes or what we'd like to see, the 51%. The Q is people who don't like this guy, people who don't think he's good. And so that's 49%. Your E is the plus or minus the 3.5 percentage points. What else do we need? Oh, the N is how many people? 1,144 people. That's our sample. And what does the P represent? So the difference between P and the other P, this is kind of like our successes, but with the little top on it, right? This is the best value of the population proportion, and this is the population proportion. So we don't really have P. P represents the whole population proportion that we're really trying to show. So our P for this one, for number 3, our P, this is the sample who said yes. Our P, this is the population proportion. This is what the little p is. So this is gonna be 54.5 is less than p, which is less than 47.5. Ta-da! That's the population proportion of p. All right. What else do we have to do? 1 through 6. Okay, so we're gonna keep going. Why are there so many? Who knows? Given the specific sample data, such as data in exercise 1, with confidence interval, which confidence interval is wider? 95% confidence interval or the 80% confidence interval? Which one is wider? I believe 95% would be, because 95% to me means what? We've got 0.25 and we have what? What's 2.5% on both sides? So this means we have all of this, right? Since we have all of this. Now, if we had 80%, right? If you have 80%, that means it's 10% here and 10% here. So we're gonna be here. So this means our range is 97.5%. And this means our range is 80%. So obviously, to me, the first one is wider. All right, so find the critical values of 90% and 99%. Okay, cool. So if we have 90%, I'm going to equals norm.inv. And we know 90 is really what? 0.9501. So 1.64 and the other one's 0.975. So that's what the critical values are. Remember, because we're cutting them in half. Oh, sorry. So 5 is 90%. So that means our critical value is going to be 1.64. And for 6, if it's 99, basically I have to take this and make it 99 and a half. And this means our critical value is 2.57, 2.58. I might as well look them up in the back and see if I did it right. Nice, correct. All right, what else we got to do? All right, 11 through 14. Let's see what we got. 11. In section 9 through 12, confidence intervals. The confidence are based on the proportions of red, orange, and yellow and blue M&Ms. Data set 32 in Appendix B. Express the confidence interval in the form of 0.0847 to 0.1453. Oh, okay. So they just want us to change this into the other form. They're already given us the answers. I thought we were gonna have to find these values and I was about to not be happy. But for number 11, we have these two values, right? We know that the low one is gonna be what? 0.0847. And the high one is what? 0.153. Right? So we need to, so this is our difference, right? This is basically the two values with the differences. So how can we figure out what they are, right? What's the error? Well, the error is going to be the same for both, which is really nice, right? The error is going to be the same for both. So to get the error, all we have to do is basically add these two things together and cut it in half. And that should be our error value. I think we did a formula like that, right? The error, oh, sorry, we subtract the difference and then cut it in half. Sorry, I'm totally fine. I'm human, I make mistakes, right? So this is our lower, this is our upper. So all I have to do to find the error is take 0.153 minus 0.0847 and cut it in half. So So 0.153 minus 0.0847. And then all I have to do, divide it by 2. So my error is 0.03415. So we know it's going to be, our error is 0.03415. And to get the other one, we just add them together to get this p-value in the middle. I'm just going to make this a plus sign. And then we can check it because it's math. So it's 0.11885. We want it to what, 3 significant digits? So I'm just going to do 0.119. So what's another way to write this, right? What's another way to write it? If I take 0.119 and minus 0.03, I get 0.08. If I take 0.119 and add 0.03, I get 0.153. That's how it works. So they want it in this specific form. So here's the form. 0.119 minus, oh, they just want the value. They don't care. They just want the value. Express the confidence in the form. No, I'm going to do it. So this, oh, so they just want the middle number. So 0.0847 is less than 0.119, which is less than 0.153. Ta-da! I believe this is what they want. This is written in a different way, but I will take it. All right, in 12, express the confidence interval of 0.255 plus or minus 0.046 in the form of this. Oh, okay. To me, it's just, oh, we need the smaller number. So for 12, we have the middle number, which is 0.255. All I have to do is add 0.046 and minus 0.046. Point 255 plus 0.046. And then we have to do the same thing, but we're going to subtract it. 0.209. Ta-da! Cool. All right. $13 and $14. Okay. I'll probably do a couple more. Here's 13. In exercise 13 through 16, use the sample data and confidence interval. Find the best point estimate of the population proportion. Identify the value of the margin of error. Construct the confidence interval. Write a statement that correctly interprets the confidence interval. Okay, so we got to write a sentence too. Wild. So, in a recent U.S. Open tennis tournament, men playing singles matches used challenges on 240. So there's our N. We got 240. Among these challenges, 88. So that's our P. Our 88 is the successful, but we're going to turn this into percentage. And to be overturned, construct a 95% confident interval. Okay, cool. So this is all we get. I know it's not a lot, but basically I need this as a percentage. So first thing I have to do is 88 divided by 240. That's my first step to figure out what the P is. 88 divided by 240. Oops. Is 0.366. I'm just gonna do 0.37. So that's P. So that makes our Q what? 100 minus 0.3, or sorry, minus 37. So our Q is 0.63. We're doing 95% interval. So we can go here. And our 95% interval is really 0.975. So we know it's got to be 1.96. That's our critical value. I don't know what else we need, but I got a lot already. So I got the data, got my P, I got my Q, I got my Z value. I think I'm good to go. I'm gonna look at the formula. Here it is. Well, that's getting N. We don't need that. Let's go up. Here we go. So this is how to get the error. Okay, we can get the error first. That's fine with me. Let's get this error. So here's the error that I'm going to get. So we know it's 1.96 square root of what? I believe it's 0.36 times 0.37 times 0.63. Remember, this is good call overturned. This is not overturned. And then we have to divide this by our N. And our N was, oh my God, I forgot. What's our N? 240. This is going to give me the error. So I should be good to go after this. So we have 1.96. Oh, I don't need the parenthesis. I remember from last time. Parenthesis. 0.37. 0.63. Divided by 240. And I have a 0.06 error, which is nice, which means it's going to be plus or minus 0.06. So this is what I think the answer is. Remember, I'm human. I make mistakes all the time. So I think it's going to be between 0.37 plus or minus 0.06. So we're going to be 95% sure it's between these two values. And what are those two values? 0.37 plus 0.06, which is, it's going to be between 0.43, and I believe this is our confidence interval. It's going to be 0.31. Let's see what it is. Oh, I have to look in the back. 0.306, and it says 0.428. I rounded, but I got it. Isn't that nice? We got our 0.06 was our error, which is what we wanted. 0.37 was, yeah, so, oh, they just wanted to spell that. I rounded mine. You have to round yours. Nah. And you could make whatever statement you like. I'd rather you guys really try to think through the statement. And 14, I'll do 14 and 19. Here's 14. The drug Apixaban. Okay, no more blood clots. I like that. So here's our N. And clinical trials, 153 adverse reaction. And they want the adverse reaction. Okay, so basically our p-value is they want the adverse reaction. So basically I have to do 153 divided by 5924. This is going to be my first percentage. Sorry, so 0.0258. I might as well be specific because the other one had a lot of decimals in it. All right, that means my Q is going to be 1 minus this. Okay, so one is 0.0258, the other one's 0.974. Q is 0.974. All right, so these are our two things, right? Right away, so our P is this percentage. What is the percentage? 2.58%. What is the Q? It's 97.4%. All we really need is the error. They want the confidence interval. All we really need is the error. So we pretty much have everything we need right away. Did they want it to what, 95%? Oh, they want 99%. So the first thing I have to do is get that critical value. Critical value is this one. It's the 99.5. So that's the 2.58. 2.58. So that's my critical value. You can think about it as the Z alpha divided by 2 squared. The Z alpha divided by 2 squared. Either way it is. I already forgot it. 2.5 something or other. Come on, open for me. Was this what we're on? Am I putting them all in candy? I just don't want to have to do it again. Yeah, 2.58. So I have my decimals already up. But basically, in order to get this one, all I have to do is change this 1.96 to 2.58. It's not a 37% chance it's working. It's now just a 0.258. This is not a 0.63. This is a 0.974. This is not 240 calls. It is 5,924. So our error for this one is going to be 0.017. So this makes our confidence interval what? We're 99% confident, right? That the nausea, right? That the adverse effects is going to be between how many people? Our P, just in case you want to know that P, is 2.58%. So all I have to do is take 2.58, right? And do what with it? 2.58 minus 0.017. Oh, sorry, that's the percentage. So minus 1.7. Because remember, these are percentages. So it's going to be between 0.88%, right? And the high number, we just got to add this 17% and 4.28%. That's the chances or the likelihood, 99% likelihood that you're going to be between this for your adverse effects. All right, so maybe I'll do one more. I did 1 through 6, 11 through 14. Let's see what 19 and 22 have in store for us. Same thing. In a recent U.S. tournament, women's playing civil matches, 137 calls were made by line judges, 133 were successful. The call returned, constructed for successful challenges. Compare this A to the percentage of such made by men. Well, I'll at least do the first part. I might as well do the first part, but they're all going to be the same like this. Like you just try your best, okay? But here's the last one. Let's get rid of the search. So here's 19. So our N is 137. We're talking 33. We're found to be successful, right? So this is going to be our p-value right away. This is what we need. So that's 0.168. So what do we know this is? This is 16.8%. So if that's yes, the Q is going to be what? Well, what's 100 minus 16.8? 83.2 is unsuccessful. And the only other thing we really need is this Z alpha divided by 2 score, but we really notice the critical value. So they wanted 99%, 99%. So we already have that. It's going to be the 2.58. So all I have to do is basically do the exact same thing I just did. 2.58. Now this is 0.168. And you can compare it to the guys and tell me what you think. And there's a lot less calls here, right? Whatever the value is. So 0.168, 0.832, 137. So our error in this case is what? 0.082. So it's 8.2%. So what does this mean for the answer? Well, we know our P, right? We know the P that we have. The P that we have is 0.168. Well, we'll look at it as a percentage. This is really 16.8%. So all we have to do is subtract the 8.2 from it and add the 8.2 from it. So here we go. 16.8 plus 8.2. So that's 25% successful. This is our confidence interval. The other one, we're going to subtract the 8.2. And here's 8.6. There it is. I'll look it up just to make sure I didn't make any mistakes on this one. The rest are on you. I'm sure you can do it. This video was super long. Sorry, there's a lot. I actually learned a bit while I was doing it, which is always good for me. This is 7. This is number 19. They say 14.7. Ooh. This one is 9. Oh, sorry, I was looking at the wrong one. So for 19, they say it's 14.7 to 33.5. That is not what I got. So we might as well look at it. So if I made a mistake, I just made a mistake on 19. Let's find the mistake, right? We're human, we all make mistakes. And let's try this again. So this will be the last one I do. Hopefully I'll find the right answer. Open tennis tournament, women's playing in singles matches used 137 calls, challenges on 137 calls made by the judges. Amongst those challenges, 33 were found to be successful and overturned. So I did 33. Let's start the whole thing over, step by step. So they got 33 divided by 137. And already I see a mistake. So this says 0.168, but the exact value is 0.24. So the P should be what? 0.24. So this is what? 24%. So if it happening is 24%, it not happening is what? Well, what's 100 minus 24? 76%. So all I have to do is the formula again. I'm going to go back to the top of the formula so I don't make a mistake. So here it is. So we know the first value is going to be that 2.58. Cool. That is what this is, our critical value. Then I'm going to do square roots, our P cubed over N. So our P is 0.24. times our Q, which is what? 0.76. We're gonna divide that, oops, we're going to divide that by our N, which is 137. And our error is not 0.082, but it is in fact oh, now my pen doesn't want to work. Cool. Oh, there we go. So it is in fact 0.09. It will let me draw. Be much happier. It is 0.09. So this value of it happening was 0.24. So 0.24 plus 0.09 is, sorry, because it's in percentages, 24 plus 9 is 33. And 24 minus 9 is 15. Let's see what the right answer is. Yep, rounded, it's correct. Sweet. Use the correct significant figures for this. Try your best on it. Hopefully, sorry I made a couple mistakes, but I really hope this was useful. This was 7.1. And yeah, try your best. Reach out to me if you need help. I know this is tough.